Be discussing the force of gravity, the force of friction, the normal force. But before we get to that, let's first talk about how you calculate a force. To calculate a force, you need to know two things. You need to know mass and you need to know acceleration. An object that has mass will only accelerate if there is a force being exerted on it. The mass should always be measured in kilograms. The acceleration should always be measured in meters per second squared. And if the mass is measured in kilograms and the acceleration is measured in meters per second squared, your force will always come out in newtons. If your mass is in grams, make sure to convert it to kilograms. If your acceleration is any other unit other than meters per second squared, make sure to switch it to meters per second squared. Otherwise, the product will not give you newtons. The most important force that we're going to talk about today is the force of gravity. Then we're going to build into the idea of something called the normal force. And finally, we're going to close out our discussion by talking about the force of friction. We're going to start off by drawing out a flat surface. It could be the ground or it could be a table. On this surface, you place a box. The force of gravity should be the first force you should always draw in any of your diagrams. The force of gravity will always push downwards. And the force of gravity is calculated by taking the mass of the box and the acceleration of gravity. You can say that the force of gravity is simply m times a, but the a is so specific, it's an acceleration of gravity, we give it a special letter, so we're using little g to define the acceleration of gravity. So your mass should be in kilograms, the mass of the box, and the acceleration of gravity should be 9.8 meters per second squared, or 10 meters per second squared, and the force will come out to be in newtons. From now on, actually, I won't write out the entire thing. I'll just write out the force of gravity by writing out this part, m times g. So the force of gravity is pushing the box down. Now, does the box actually go down? No. In this case, the surface is strong enough to prevent the box from going down. If the surface is strong enough to prevent the box from going down, then that means the surface is exerting a force on the box as well. The force of gravity is trying to push the box down, but if the surface can hold the box in place, that means the surface is pushing the box in the opposite direction. How strong is this force, and what do we call this force? We call this force the normal force. F subscript n represents the normal force. It represents the force that a surface exerts on an object in response to all of the forces that the object exerts on the surface. So it keeps the object in equilibrium, keeps the object at rest, or keeps the object on top of the surface. If the surface wasn't strong enough, then the surface would break and the box would go straight down because the force of gravity would be too strong for the surface. But in this case, we're saying the box stays on the surface. That means the normal force that the surface is exerting on the box has to be just as great, just as strong as the force of gravity. So in this scenario, the normal force is equal to the force of gravity. It is in the opposite direction, but just the same strength. That's why I'm trying to draw these arrows to be identical. They should be drawn the same length. Is this an example of Newton's third law? Newton's third law says every action has an equal and opposite reaction. So is this an example of an equal and opposite reaction? The answer to that question is no, it's not. Even though the forces are equal and opposite, they're both being exerted on the same object. For something to be an example of Newton's third law, which is that every force has an equal and opposite reaction, the two forces, the action and the reaction, must take place on two separate objects. Let me give you an example. If you have a rocket ship, and you turn on the rocket ship engines, and the engines fire downward. So they're taking all the gas particles and they're pushing them down. So all of these gas particles are being forced downward. So there's a force on all the gas particles downwards. What do you notice happens? The rocket ship goes upwards. So that's an example of Newton's third law in action, equal and opposite reactions. There's a force on all the gas particles down, and in response, there's a force on the rocket ship upwards, which causes the rocket ship to go up. So this would be an example of Newton's third law. Every action has an equal and opposite reaction. Here's another example. The force of gravity, where does it come from? It comes from an object that has mass. So let's take two objects. One will be the Earth, the other will be the Moon. So this is the Earth. I'm going to say the mass of Earth is labeled as m1. The mass of the Moon is labeled as m2. What do we notice? We notice that there is a force of gravity that exists between the Earth and the Moon. They're both pulling each other. They're both pulling each other equally. The Earth pulls the Moon towards it, the Moon pulls the Earth towards it. Now, why is this happening? Where does the force of gravity actually originate from? On the subatomic level, there are particles called gravitons. Every object that has mass trades gravitons with other objects that have mass. These particles, these gravitons, are literally... Excuse the bell. These particles called gravitons are literally traded with each other like you're playing baseball, you're playing catch with a baseball. So they're throwing these gravitons to each other and they're catching them. So this constant trade of gravitons takes place. The more mass you have, the more gravitons you can trade with your partner. So that's what generates the force of gravity, this exchange of these subatomic particles called gravitons. How do you calculate the force of gravity? Well, to calculate the force of gravity, you need to take into account both masses, m1 times m2. You need to take the product of both masses. That's the first thing you've got to do. You've got to take the mass of the first object, multiply with the mass of the second object. What else do you need to do? You need to know how far these two objects are from each other. How far is the center of object 1 from the center of object 2? We call that distance, r. And the equation has r squared in there. The reason why it has r squared in there is because when the force of gravity comes outwards and it attracts objects towards the center, it comes out like a sphere. It doesn't come out like a circle. You need one last component. That's called the gravitational constant. This is a number that will be given to you by your teacher. It's 6.67 times 10 to the negative 11 newtons meter squared over kilogram squared. But this is a number that you can find in the book. This is not the most important part, even though it's very important. It's very useful for our equation. What I want you to focus on is that to calculate the force of gravity, you need to know the mass of the first object, the mass of the second object, and how far those two objects are from each other. Now, why is it that the distance between these two objects is called r? Why not d? Why not x? Why not y? Well, the reason why it's called r is because one object starts to rotate around the other object. Like the moon rotates around the Earth. So when it rotates, that distance between the two becomes the radius. So we use r. So if you were to double the mass of one object, the force of gravity would double. If you double the mass of both objects, the force of gravity would quadruple. If you were to double the distance between the two objects, the force of gravity would decrease. By how much? It would decrease to 1/4 its original value. If you were to double this distance is being squared. So the entire answer decreases to 1/4 its original value. If you were to triple this distance, meaning you make the distance between the two planets 3 times as far, then 3 squared is 9. That means this whole answer will become 1/9 its original value. So the force of gravity decreases to 1/9 its original value. So that's a brief explanation on the force of gravity and where it originates from. This is an example of Newton's third law. Every action has an equal and opposite reaction. These two forces are equal and opposite, and they're being exerted on two separate objects, just like the rocket ship in the previous example. The equal and opposite reactions must take place on two separate objects for them to be considered as part of an example of Newton's third law. If you ever need to calculate the force of gravity using these variables, make sure that the masses are in kilograms, and make sure that the distance between the two planets or between the two objects is in meters. If you do that, your final answer will come out in newtons. So make sure the masses are in kilograms and the distance is in meters. And the force will come out to be in newtons. So back to our original idea. If you place an object on a flat surface, the force of gravity and the normal force will be same strength. The normal force is the force that the surface exerts on the object in response to the force that the object exerts on the surface. In this particular case, the force of gravity is pushing the object down, so that if the surface can keep the object in place, that means the surface is exerting an equal force upwards that is just as strong as the force of gravity. Now let's change our scenario. We'll take the same box, but this time we're going to pull it with a rope. Same box, but now the box is attached to a rope. It's kind of like a toboggan or a sled. You're trying to pull this sled sideways, so you take the rope, attach it to the sled, and you're pulling it on your shoulder, and you're walking to the right. So that means you're exerting a force upwards. We're going to call that force Fa, because it's an applied force. We're going to call it Fa. You can call it Ft for tension force, because it's a force that exists in a string or in a rope. You can call it tension force. You can call it whatever you want to call it. Today I'm just going to call it Fa for applied force. So this is taking place at an angle theta. How does this change our normal force? Well, the first thing you've got to do is whenever you get a vector at an angle, you should break it down into its x and y components. If you're pulling with a force Fa at an angle theta, that means you are pulling to the right and you're pulling up. So this rope is actually pulling the box to the right, but it's also pulling the box up. It's doing two things at the same time. The sideways component, the x component, I'm going to call it Fax. It's the x component of Fa. The upwards, I'm going to call the upwards part, I'm going to call it Fay, because this is on the x-axis, this is on the y-axis. Keep in mind, I'm using the traditional XY coordinate system that was taught to us in our math classes, where the x-axis is parallel to the horizon and the y-axis is perpendicular to the horizon. How do you calculate the Fax? Well, this is a right triangle, so if you need to find the adjacent side, you use cosine theta. Cosine theta is equals to adjacent over hypotenuse. This is your hypotenuse, this is your adjacent side. You multiply the Fa, and you've got Fax. Fax is going to be Fa times cosine theta. You can put any numbers you want to, depending on your teacher's problems that they give you in class. I'm going to leave the letters in there, just so you understand the concepts and how to get the final answer. At the end, you can put in any number you've been given. So Fax is simply going to be Fa cosine theta. How do you find Fay? Well, you use the same idea, except instead of cosine theta, you're going to use sine theta. So, the gist of this example is that when you're pulling with a rope at an angle theta, you're actually pulling to the right and you're pulling up. So how does this impact our normal force? Well, the force of gravity is always drawn downwards. That's the first thing you should draw. You should say the force of gravity is always down. So how does the normal force get impacted? Well, you've got to ask yourself a question. Is the box pressing against the surface with a greater force or a weaker force than in the previous example where there was no rope? In the previous example, there was no rope, so the box was being pressed against the surface because of the force of gravity. In this example, there's a rope. The rope is pulling upwards. It's pulling the box upwards. So the box doesn't press against the ground as hard. The total force with which the box is pressing against the ground, the sum of all of the forces in the y direction, meaning the total force with which the box is pressing down on the y-axis, is the force of gravity minus Fay, minus the vertical component of the rope. The rope is pulling up, so I'm going to subtract this out of this because the force of gravity is pulling down, but the rope, which is connected to the box, is pulling up, so it's pulling the box up. So these two forces are going against each other. That means the box is not going to press against the ground as hard as it was when there was no rope. And instead of writing Fay, I'm going to write Fa sine theta because that's what Fay stands for. Now, if this is the total force with which the box presses down, if you need to find the normal force, and the definition of the normal force is it's the force that the surface exerts on the box in response to the total force that the box is exerting on the surface, then the normal force in this scenario is going to be weaker than what it was in the previous scenario when there was no rope. The normal force is going to be equal and opposite to the total force pushing the box down. The box is in equilibrium. That's why these two have to balance each other out. The total force pushing the box down has to be the same as the normal force which the surface is exerting on the box upwards. Let's change the scenario again. We're going to take the same box, but now, instead of pulling the box up and to the right, we're going to push it down and to the left. So instead of pulling upwards, we're actually going to push down. It's still Fa, and the angle that it makes with the horizon is still going to be labeled as theta. So this is kind of like a lawnmower. This is the lawnmower handle, this is the lawnmower, this is the grass. So you're pushing down on the lawnmower handle, and when you push down on the lawnmower handle, you're doing two things. You're pushing the lawnmower down, and at the same time, you're pushing the lawnmower to the left. In the previous example, we had a rope pulling up and to the right. Now we're pushing down and to the left, and we're going to see how this changes our normal force. Well, first things first, whenever you get a vector at an angle theta, always find out its x component and y component. You're going to find the x component the same way. Fa cosine theta. You're going to find the y component using sine. Fa sine theta. The question is, how does this impact the normal force? Well, first things first, we should always draw the force of gravity. Now, you've got to ask yourself, is the box pressing against the surface with a greater force or a weaker force than in the previous example? In the previous example, remember, the force of gravity was pushing down and the rope was pulling up. In this example, the force of gravity is pushing down like it always will. But now, this Fa, the applied force, is actually pushing down as well. So there are two forces that are pushing this box down against the surface. So the box will press against the surface with a greater force than it did in the previous example. So the total force in the y direction, meaning the total force pushing the box down, is the force of gravity plus Fa sine theta. Because both of these forces are pushing the box down. If the total force pushing the box against the surface is mg plus Fa sine theta, because both forces are pushing the box down, then what's the normal force going to be? Well, remember, the normal force, if the surface is strong enough, that means the surface is preventing the box from going down. That means the surface must be exerting an upward force that equals the total force downwards. So the normal force has to be just as strong as this to keep the box in place. So this time, I'm going to draw the normal force much longer than I did in the previous scenario because now the normal force is greater. The normal force will be equal to mg plus Fa sine theta. The total force pushing the box down is mg plus Fa sine theta. So the total force pushing the box upwards, the force that the surface is exerting on the box, which we call the normal force, has to be just as strong. So that's how you find the normal force if you're pushing down and to the right. We're going to change the scenario once more. Now, I'm not going to be on a flat surface. So far, I've discussed problems with you where a box is on a flat surface. Now I'm going to change it. Now I'm going to put the box on an inclined surface. So here you go. You got an incline. How steep is this incline? It's that steep. Whatever that angle theta is, 20 degrees, 30 degrees, 35, 40 degrees, however you want to make it. So there's an inclined surface, and it's theta. That's the angle of inclination. That's how steep it is. You're going to place a box on here. And remember, so far we haven't introduced anything about friction. So far everything has been without friction. So when you put a box on the surface, you know that that box is going to slide down. It's going to slide down the surface. Now, when it slides down the surface, we know it's sliding down because of gravity. But is all of gravity pushing the box down the incline? Well, think about that for a second. Take your incline and increase it from 20 degrees to 30 degrees, from 30 degrees to 50 degrees, from 50 degrees to 60 degrees, to 90 degrees. At 90 degrees, the box is going to come straight down because all of gravity is going to push it downwards. It's going to be in free fall. So if at 90 degrees, all of gravity is pushing it downwards, then at any angle below 90 degrees, that means not all of gravity is going to push the box down the incline. Only part of gravity is going to push the box down the incline. The force of gravity always points down. Question is, how do we break up the force of gravity? Well, all we're going to do is we're going to tilt our xy coordinate system. So far, we were using the traditional xy coordinate system that was taught to us in our math classes, where the x-axis is parallel to the horizon and the y-axis is perpendicular to the horizon. But now I'm going to change it. I'm going to make my x-axis parallel to my plane and my y-axis perpendicular to my plane. All I did was, if the incline has been tilted, I've gone ahead and tilted our xy coordinate system to match up with it. So it's kind of like you took your sheet of paper and you've tilted it. So you're still dealing with the same problem you were earlier. So what are you going to do? How is this going to help you break down the force of gravity? Let me draw this a little bit neater. This is my new x-axis. I'm trying to draw it so it's parallel. Okay, so you're tilting your xy axis. So this is your new x, and this is your new y. And you've tilted it by the same angle theta. So this force of gravity, if you were to draw it on this new xy axis, it would look like this. This is being represented on your xy coordinate system. Why is it being represented? Well, because tilting the axes is going to help you break this vector down into its two components. There is a component pushing on the y-axis, perpendicular to the surface. And there is a component that pushes on the x-axis, parallel to the inclined plane. So here's the force of gravity. Part of force of gravity is pushing on the y-axis. Part of the force of gravity is pushing on the x-axis. What does this mean towards our drawing? It means that part of gravity is pushing the box against the surface. And part of gravity is pushing the box down the surface. When you draw this is a representation of this vector addition problem right here. When you draw this, make sure that your y component is perpendicular to the surface, and make sure your x component is parallel to the surface. Let me just tidy up my drawing here. Okay, so this is the force of gravity. This is the y component. This is the component of gravity that's pushing you into the surface. This is the component of gravity that's pushing you down the surface. So this drawing has been duplicated over here. Force of gravity always points down. Then you break it up into its two components. Remember, we're now working with a tilted xy coordinate system. If this is the angle theta, then geometrically speaking, this is theta. Now, why is that the case? Well, think about it this way. If you were to take this base connected to the black line, let's say this is 40 degrees. If this is 40 degrees, what angle does the blue line make with the black line? Well, these two are perpendicular to each other, so this should be 90 degrees. If this is 40, this is 90, what must this angle be, the angle that exists between the blue line and the black line? Well, remember, all three angles have to add up to be 180 degrees. So if this is 40 degrees, this is 90 degrees, then this has to be 50. If this is 50, then this is 40, same as this angle. If this is 50, this is 40, because remember, the blue and the red make 90 degrees with each other. So if this is 50, this has to be 40. And remember, we started off with 40 over here. I was just giving you an example. I was trying to show you that if this angle is 40 degrees, this angle right here is 90 degrees. If this is 40, this is 90, then this is 50, because all three have to add up to be 180 degrees. And if this is 50, then this is 40 degrees, which is the same as this. So I'm just trying to prove to you that this theta is the same as this theta. Okay, so how are we going to find out the y and the x components? We're going to use our trig functions. This is a right triangle, because this is a right triangle. If this is the hypotenuse, then that makes this your adjacent side. So this is your adjacent side. How do you find the adjacent side, and what do you call it? Well, if the hypotenuse is mg, I'm going to call the adjacent side mgy. I'm going to call it mgy because it's on the y-axis. It's on our new y-axis. And how do you find out what it is? It's mg cosine theta. If mg is your hypotenuse, the adjacent side is the hypotenuse times cosine theta. How did I come up with that? I simply said, look, cosine theta is adjacent over hypotenuse. Cosine theta is this side over the hypotenuse. And this side I'm calling mgy. So adjacent over the hypotenuse. So how do you find the adjacent side? You bring mg over. So that's how I came up with mgy is equals to mg cosine theta. And I'm going to do the same thing to find the x component. Except instead of cosine theta, I'm going to use sine theta. Sine theta is equals to mgx over mg. I'm going to call this side mgx. Why am I going to call it mgx? Because it's on the x-axis. It's parallel to the x-axis. And how do you find it out? Well, sine theta is opposite over hypotenuse. Sine theta is opposite over hypotenuse. When you solve for mgx, you take the mg over. Mg sine theta is equals to mgx. So that's what mgx will be equal to. It's going to equal mg sine theta. It's going to equal the hypotenuse times sine of the angle. So now, the question comes up, what is the normal force? Now remember, the normal force is the force that the surface exerts on the object in response to the forces that are pushing the object against the surface. So you can ask yourself, you have three forces right here. Which one is solely responsible for pushing the box against the surface? And the one that's solely responsible for pushing the box against the surface is mgy, is mg cosine theta. This is the force that's pushing the box against the surface. Here's the force of gravity. Only part of the force of gravity is pushing the box against the surface. The other part is pushing the box down the surface. So if mgy is the only force pushing the box against the surface, the normal force will be just as strong as mgy. The normal force will be equal to mgy, or whatever mgy stands for, which is mg cosine theta. So in inclined surfaces, you have to tilt your x and y coordinate system. And when you tilt your x and y coordinate system, remember to draw your force of gravity. Always, it should go downwards. Remember, this angle theta will be the same as this. Break up your force of gravity into its y component that should be drawn perpendicular to the surface, and the x component that should be drawn parallel to the surface. Because remember, I've tilted my x and y axis so that the y is perpendicular to the surface and the x is parallel to the surface. This will be called the y component. This will be called the x component. This is the component of the force of gravity that's responsible for pushing the box against the surface. This is the component that's responsible for pushing the box down the surface. Once you have your right triangle, then you've got to use your trig functions, sine and cosine, to find the strength of this force and the strength of the x force. And remember, the normal will be equal to mgy. In our next video, we're going to be talking about the force of friction. So far, we haven't spoken about the force of friction. In the next video, we're going to introduce the force of friction, and we're going to start from the beginning, where a box is on a flat surface. Then we're going to add a rope in the scenario and talk about the force of friction. Then we're going to talk about the lawnmower and the force of friction. And finally, we're going to come back to that last slide about an inclined plane and how the force of friction comes into play.